So we're going to talk about orbits, and in particular satellite orbits, and how we can predict satellite orbits around larger masses such as Earth or any of the other planets or moons or even asteroids out there, and how we can so actively predict what those orbits are going to look like. We can do so in part by the understanding of conservation of angular momentum. Now, I was going to put a demonstration together for this one, but the folks at MIT have already done a phenomenal job explaining and demonstrating what angular momentum is and why it matters to us. So we're going to go ahead and play that video, and then we'll talk at the end.
When I hold the spinning wheel, nothing crazy happens. But when I flip it, I spin. Flip it back, and I stop. Flip it, I spin. So the question is, why am I spinning? So I have to force the wheel to turn over. Now Newton's third law says that for every force, there's an equal and opposite force acting as well. So when I force the wheel is applying force equal and opposite onto me, causing me to turn. So the same thing applies when I'm on the ground, but the friction between my shoes and the ground stop me from spinning. So another way to explain what's going on is through conservation of angular momentum. Now, angular momentum is something that tells you how hard it is to either start or stop something from spinning. And it depends on two things. One, how fast it's spinning. We call that the angular frequency. Two, its shape, or what we call the moment of inertia. So this wheel is rotating counterclockwise. Now I'm gonna teach you a trick. So get your right hand, and I want you to curl your fingers in the counterclockwise direction. And you see that your thumb is pointing upwards. We'll call that the positive direction. So see, this wheel has positive angular momentum with a magnitude of L. Angular momentum is conserved. That means that as long as there are no outside forces, the total angular momentum of the system always stays the same. So when you flip this thing over and do the right hand trick, your thumb points down or in the negative direction. So the angular momentum of this wheel is now negative L. So the whole system, me, the turntable, and the wheel starts out at negative L. But when you flip the wheel now has positive L. So the whole system needs to stay at negative L because of conservation of angular momentum. So I need to spin with angular momentum of negative 2L. That's why I spin the other way.
So that's a great explanation about the conservation of angular momentum. So the demonstration was great with a bicycle wheel, but a bicycle wheel is perfectly round. When we talk satellites, typically satellites are in some sort of an elliptical pattern around their orbiting body. So that complicates the calculations a lot more. Now, I'm not going to go into the definition of the calculations and the proofs because that's very complicated and we simply do not have the time in this forum. But what I can say from a high level is that this theorem states that angular momentum is conserved if no other net torques are applied or involved in the system, which is true for space and our orbits out there. So what that basically says is as distance from an object increases, its speed proportionally decreases. So that means that as a satellite is further away from its orbiting body, it's going to be going slower. As it approaches its nearest approach, it's going to be the fastest in its orbit, and it's going to circle back around and it's going to slow down again. So all that to say is we use this predictive analysis to calculate our orbits, and that's how we avoid all of our satellites hitting it in mid-flight. And the same can be said for our Earth's orbit around the sun, right? We're essentially a satellite to the sun in perspective of size and just brute mass. So the Earth's orbit deviates around the sun approximately 3.4%. So that means that at certain times of the year, the Earth is actually traveling slower in its orbit to the sun, and other times of the year, we're traveling faster, as is identified in this illustration.